which is the simplest type of learning that you will ever meet. So if you're in a real hurry, instance-based learning is hard to beat. So we're going to start with the simplest type of instance-based learning. It's called the K-nearest-neighbor algorithm. This is the oldest real machine learning algorithm in the world. There were things from statistics, of course, going back to the beginning of the century and whatnot, but none of those had the ability to learn to grow arbitrarily with more data. So in some sense, they weren't real machine learning algorithms. They were just fitting parameters to a model. The first learning algorithm that wasn't just fitting parameters to the model, but could learn infinitely more if you gave it infinitely more data was K-nearest-neighbor. Okay? This was something that was invented in the 1950s and was originally very obscure, but then became very widely studied. In fact, it is one of the most widely studied types of learning of any. More generally, K-nearest-neighbor is an instance of what is called instance-based learning, which is learning by remembering specific instances. Also called exemplar-based learning or memory-based learning because you're just remembering things, or sometimes lazy learning, although as we'll see that is a somewhat more general notion. Sometimes analogy-based learning because you're doing analogies between the new and the old. So there's a whole kind of like galaxy of learning methods here. We're just sticking with the general moniker instance-based learning. Okay? And then finally we will look at the application. Probably the single most important application of instance-based learning in the world today is recommender systems. So we're going to see how that works. In particular, how you do collaborative filtering using instance-based methods. Okay? And then this will lead directly to your second project, which is to do the Netflix prize. Okay? A little caveat: we're only using a subset of the data. Okay? Because even then, it's going to be actually two caveats. Don't run that at the last moment, because doing it naively will be expensive, right? You won't run in 5 minutes. But number two, because of that, we self-selected the data. We're not giving you the real Netflix data set. We're giving you a subset, and the subset was deviously selected by us to be interesting. In particular, to be dense in terms of the ratings available. So when you run your project and you're getting incredibly high accuracy, don't go out and do a startup because you think you have a new great, just a navigational warning.
I'm just pumping us up to make us feel better.
No, exactly. So like, wow, I beat them. I beat people. Like those people who spent 2 years working on this. I'm doing better than them right off the bat. I'm a genius. I deserve $1 billion. So, just a little warning there.
Burst our bubbles. Burst our bubbles.
Which is not to say that you couldn't take it from there and become a real champ. In fact, the first time that I used this project was when the Netflix data came out. It was the year when the Netflix prize was actually active. And there was actually somebody in this class who learned machine learning for the first time in this class, and then he continued to play after the class was over, and he wound up being a member of one of the winning teams. Which shows that you can, right? So you could go straight, Netflix of course is now closed, but you can go from this class to, a Kaggle competition and make hay there. Okay? I saw a talk by Anthony Goldblum, the CEO of Kaggle, a couple of weeks ago, as I already mentioned, and he said that the two biggest characteristics of Kaggle winners are, what? Number one, persistence. Meaning, you were number one on the leaderboard and somebody just passed you. You go back and you hack on it until you're back at number one. Right? It's never accept, defeat. This is number one. And number two, which makes sense, right? The more persistent ones are the ones who tend to win in the end. Number two is creativity. Creativity in coming up with the right features to describe the problem. Okay? Another thing he said that was very interesting is that, why don't the experts in the domain win the competitions more? He said that having expert knowledge is actually a double-edged sword. On the one hand, it can help you come up with better features, and at the end of the day, coming up with better features is half the game, right? And that's where creativity goes. On the other hand, the experts tend to have preconceived notions about what's possible, which prevents them from often seeing features that will win, because according to their expert knowledge, those features are wrong. So there you go. So there's power in knowing, and there's also power in not knowing. So I don't know what the moral of the story is there, but hey. Okay, so let's start with the basic idea of the K-nearest-neighbor algorithm, or of instance-based learning in general. This is an algorithm. You know what the learning time of the K-nearest-neighbor algorithm is? Oh well, let's say that the number of examples is n, right? And you look at decision trees, for example, it's and rule induction, right? It's O of. Now, you've done that question by now, haven't you? Usually as a heuristic in these assignments, it's better to do the math questions first, because the time that they take is usually smaller and less and has less variance, right? And then you can go and do the programming project. So, okay, I won't answer that question for you, just in case you haven't done it yet. But on a good day, you will have linear running time, right? O of n. You agree? If your learning algorithm is linear in the size of the day, you're in pretty good shape, right? If your learning algorithm is n squared or n cubed over n to the 4, Google might not want to hire you, but if it is order of n, they might. Okay, there's one way to look at this. Right? Or Facebook or Microsoft or Amazon. But guess what, and an even better would be something like, logarithmic, log n. Okay? Now, what would be even better than that? Constant, right? O of 1, right? Constant time would be amazing, right? We actually have developed algorithms for a lot of things that are constant time, subject to the data being IID. But nearest neighbor is even better. You know what the running time of nearest neighbor is? This is the first and last time in your entire life that you're going to see this. The running time of nearest neighbor is O0. You know why? There's only one way the runtime of an algorithm can be O0. What is that?
Lazy algorithm.
It does nothing, right? Anything that it does takes time, right? So the beauty of nearest neighbor, and that's why it's also called lazy learning, is like, nah, I'm not going to do anything with that database. I'll just let it sit there. I'll just go to the beach and let the data sit there, right? This is the power of laziness. The amazing thing about laziness is that for humans, it's a bad idea, but for algorithms, a lazy algorithm can be more powerful than an eager one. So the basic nearest neighbor algorithm at learning time consists of doing nothing. You just let the database sit there on the disk, okay? But now, what do you do when query instances come along, right? Now somebody's asking you, let's say you have a database of patients, right? And you didn't do anything, right? So you didn't go to med school, right? It's like, Frank Abbott, you guys know like the movie Catch Me If You Can, right? This guy who just faked being a doctor for 2 years and got away with it, right? And the scary thing is, and he had like a fake Harvard diploma on his wall or something like that. But the scary thing is that he was one of the highest rated doctors in that hospital. Which makes you wonder, right? But suppose that you were sitting in his office, actually not in his office, right? He went into the office of a doctor that was away, right? And pretended to be him, right? So let's suppose that you're there, right? And all you have is a file cabinet, right? With the past patients of the doctor, right? Oh, this person had these symptoms and she had diabetes. This person had these symptoms and he had, whatever, the flu, right? And then comes a new patient, okay? And there you sit. You don't know anything whatsoever about medicine. You've been lazy, right? Because that's the whole idea here. You just have the file cabinet with all the patient, symptoms and test results and the outcomes and the diagnosis. So what do you do?
Try to match.
Exactly. Find the most similar, right? You don't know any better, right? You don't have a lot of time, right? So you just find the most similar patient to the one that you're seeing now. And you guess that the diagnosis is the same. Right? That's the basic idea in nearest neighbor. Really simple, and yet, as we will see shortly, shockingly powerful. Right? That's why also this is called memory-based learning. You just remembered stuff. Okay? So, when you get a query instance, you find the nearest training example, which is why this is called the nearest neighbor algorithm. It's finding the nearest neighbor, and then you just assign the class of the nearest neighbor to the query. That's it. Okay. At test time, this could actually be expensive, right? Because you have to run through the data, right? And there's efficient ways to do that. We'll talk, a little bit about that in a while. But it's expensive, but it's still simple, right? So in terms of your implementation time, this is an algorithm that you can implement very quickly, right? Which is why we picked it for your second assignment. That coupled with the fact that there's a very compelling real-world application in recommender systems. Now, there's any questions so far? I mean, who would have questions about this, right? It's just, too simple. But now the first important generalization of this is the K nearest neighbor algorithm, right? Most people don't use nearest neighbor, they use K nearest neighbor. And from the name K nearest neighbor, you can probably guess what the algorithm is. So tell me what the K nearest neighbor algorithm is.
Recombinate neighbors and then just
Yeah, so let's say I'm doing the 3 nearest neighbor algorithm. Usually for 2-class problems, you use an odd number so that there are no ties. Okay, so say I'm using the 3 nearest neighbor algorithm. I go to my file cabinet, I find the 3 closest, right? And then what do? I vote, right? If 2 of them say diabetes and 1 of them says malaria, then diabetes wins. Okay? Very easy, right? What would I do if it was a regression problem? Right, so I'm trying to predict, how much you will spend on my credit card if I offer it to you, and and the 3 nearest neighbors are, $1,000, $2,000, and $3,000 a month. Just do the average, right? So simple as it gets. Okay. So just the simple thing of going from 1 nearest neighbor to k nearest neighbor, again, it's a very simple change, and it amortizes the work that you're already doing anyway, for the most part. But as we'll see shortly, it makes the algorithm much more powerful. Okay, in terms of what it's able to learn correctly. Okay, so very simple. Questions?
How do
Want to do a weighted mean?
Exactly. So the key question in all of this is like, what makes 2 things similar? And this is really where the whole every type of learning has something where all of your smarts go. In the case of instance-based learning, it's the similarity function. So we'll talk about that shortly. Right? It's a very important question. The answers can range from the super simple to to huge programs just to do that. Yeah. Mm-hmm.
What if you get something which is not similar to anything you have seen?
Well, in the basic nearest neighbor algorithm, you will always return something, right? If your database just contains 1 object, well, that will be the closest object to whatever comes up. So there will always be an answer. I think the more important question is like, well, how bad could that answer be? And the answer is, it could be very bad. So we're going to worry a little bit about that, in a bit as well. Yeah. So far, there's no guarantees that this will do anything useful. We'll see both what the strengths and weaknesses are, and what to do about the weaknesses, which people have been researching for decades. Okay? In particular, we're going to meet something very important called the curse of dimensionality, which is the single biggest problem in machine learning after overfitting. And just like overfitting, the curse of dimensionality affects everybody, but it affects instance-based learning particularly badly, which is why we're going to introduce it here. And then see what we can do about it. Somebody else have a question? Mm-hmm.
The question was, the similarity function can produce bad results. Is there a way to produce similarity certainty? So
This is machine learning, so there's never certainty. Right? Remember, you're always gambling. Right? There's always that element of luck in it. But there are certainly, you can have much better or worse similarity functions, and there are ways to figure out what's better and what's similarity functions. So we'll talk about that in a bit. Yeah.
No, I think it's a follow-up on the question on if this is whatever value you assign first, that was the closest nearest neighbor or k nearest neighbor.
Mm-hmm.
I'm assuming that this assigned value can change with time.
No, but that's a different issue, right? For them, we are doing things here it's lazy, but it's batch mode, right? So this is not online. I gave you the database, right? And you just can use that database. So the answer will never change.
You know your universe.
Yes, it's like, like every new case that we have to classify is like a new patient coming into the doctor's office, right? Because, you're Frank Abagnale Jr., you don't know what happened with that new patient. Maybe they died, right? If from each patient then there was an autopsy or whatever, and you added that patient to your database, right? Then that would be online learning, and then your diagnosis might change over time. Somebody else have a question back there?
You answer.
Okay, all right, so before we go into all these important details, let's just, take a step back to consider what are the pros and the cons of doing this type of learning. Well, we already saw one of the pros, which is that training is blindingly fast. Although, ironically, when we come to the more sophisticated versions of this, surprise, they start to do more at training time, and they often wind up being more expensive than, say, decision tree induction. So, training is very fast, but training. Here's another really important one. As we will also see shortly, despite the simplicity of the algorithm, you can learn arbitrarily complex target functions. You can actually approximate arbitrary target functions, for example, in Euclidean space, better than a decision tree learning. It's almost not fair, right? It's lazy, and yet it does better than the decision tree learning. But this is, of course, only one side. Here's another one. Because I'm remembering the data, I don't lose information. Decision trees rules, they lose information. Once you have the decision tree, right, it doesn't contain all the information that was in the original training set. Same thing with neural networks and other things that we'll see, which sometimes might be a problem. Right? In the case of reinforcement learning, you still have the database, you remembered everything. Okay? So that can be important. So those are the advantages. Now for the disadvantages. At query time, this will typically be much slower than something like decision tree induction, right? Because decision trees, you just have to sort your item to a leaf, and that's like roughly logarithmic, right? So it's fast. Whereas nearest neighbor, the naive version actually is order of the size of the data. And you can make it faster, but what this means is that if you want to do something like, high frequency trading, do people know here what high frequency trading is? These people using machine learning algorithms to trade on the stock market in a fraction of a second. Right? Whoever's fastest wins. Right? So there's a very big trade-off between having an accurate model and having one that is, if your model is better than mine, but I take, a hundredth of a second to execute and you take 200ths of a second, I win because I do the trade and the price goes up. So when you try to buy it, you've already lost the advantage. Okay? So for applications like that, you probably don't want something like this. You might think that, for example, controlling robots in real time would not be a good candidate for this, but actually are instance-based approaches to doing real-time robot control. You can actually make it efficient enough that, if you have to do decisions that say, 10 per second to control, the joint angles, the torques of the robot arm, you can actually do that. Okay? But nevertheless, the speed at query time can be an issue. Another one is that it takes a lot of storage, right? And in fact, this was the reason why when the algorithm was initially proposed, people were like, this is just a crazy theoretical notion. Why don't these, theoreticians stop wasting everybody's time? Because back then, in the 1950s, memory was ferrite cores, right? It was like little magnetic rings. And the idea like storing your entire data set, even though an entire data set would be just maybe 100 or 1,000 examples, but you couldn't store that in your, 6K of memory. Okay? But then guess what? Then memory started to get better, and so this was an entirely practical algorithm. So there's a lesson in that. Nevertheless, it still takes a lot more storage than something like a decision tree. Although there are ways to try and reduce the storage, and we will look at that as well. But the most important one, and really the Achilles heel of these methods, is that they are easily fooled by irrelevant attributes. Right? If there are a lot of, decision trees tend to not be fooled by relevant attributes because they have low information gain and they just get ignored, right? In particular, if you also do a significance test or post-pruning or something like that. When you're doing these similarity-based methods, if there are relevant attributes, so things might look similar just randomly, right? They were similar in attributes that didn't matter, and then you make the wrong decision because of that. And the more general problem, that this is kind of like one face-off is the cursor dimensionality, so we will spend some time looking at that, okay? Mm-hmm.
But wouldn't irrelevant attributes give me a bad distance calculation?
That's the problem, right? Is that irrelevant attributes can make things that actually have different classes look more similar than things that are of the same class. Irrelevant attributes are really just adding noise to your distance function. But if what you have is 9 relevant attributes and 1 irrelevant one, then maybe that's not too bad. But what often happens is that you have 1,000 irrelevant attributes and 10 relevant ones, and then the noise completely swamps the signal. And nearest neighbor just is making random guesses, essentially. Whereas a decision tree learner, would happily just, one hopes, find the 10 good ones and ignore the others. Yep.
I think K-near, if you're using nearest neighbor, if you find probably an exact match in your database, and that has like noisy class prediction, then is that also a problem?
No, yeah, but this is a problem for all machine learning, right? So if you have an example that has the wrong class, then this will inherit the wrong class.
But would decision tree perform better in that case?
Well, yes, because the decision tree, remember, usually doesn't make decisions just based on one example. It makes it based on a whole region, where hopefully there's a majority of the right kind of example. Okay? But again, we have something analogous in K-nearest neighbor, which is K. If I make the K large, then your decision is based on a larger area. So, so we are not without recourse there. If the data is very noisy, I just need to use a bigger K to do a bigger average that will be more robust. The problem with that is that I'm losing detail. Right? So like making decision over wider and wider areas. In particular, if I make the K equal to N, guess what nearest neighbor turns into? It's just guessing the most frequent class for everybody. Which is not a totally stupid thing to do, but obviously, that's not what we're here for. Yeah.
So I have an example that I think is like an irrelevant attribute. So in a movie recommender, you're looking at all the properties of a movie. The runtime may not be relevant to you. Like it may not matter that a movie is 96 minutes long, and it's the nearest movie to it is also 96 minutes long. That's usually not a criteria for picking a movie, but
Yeah.
that's an attribute that where nearest neighbors would say, oh, these movies are really similar.
In fact, even other properties of the movie are often not very indicative. But let me give an even better example. Imagine trying to do your current assignment using nearest neighbor by similarity on the things that people clicked on. What a stupid idea, right? Because most of the clicks are not that informative. Right? Most of your clicks are relevant, and yet this nurse is like, oh, you clicked on a lot of the same things, so it must be about to leave at the same time as that other person. Right? And it's also very high dimensional, right? Again, it's not an accident that we asked it to apply decision trees to clickstream prediction and a nearest neighbor for collaborative filtering, because that is indeed, in reality, the methods that tend to be better for each of those things.
Is there also some recommendation like if we should run the for set which has a small number of attributes compared to large number of attributes?
It's not that simple, right? The answer is always, in machine learning, it's not that simple. Because I'll give you a counter example. Nearest neighbor is very good for things like character recognition. I mean, like the state of the art for that is neural networks, right? Deep learning, and then we'll get to that. But nearest neighbor is shockingly good at things like, like the post office, right? Since this recognizes zip codes, right? This is high dimensional, right? Like every pixel is a dimension. And yet nearest neighbor does very well there. So that's a counterexample to what you're suggesting. Can you think of why nearest neighbor might do very well there, even though it's high dimensional? There's a very interesting answer to this.
Because the distance function is very simple.
Is very what?
The distance function in that pixel example would be very simple.
Well, let's just say that the distance function is Hamming distance on the pixel being black or white. Right? This is like the simplest distance function you can imagine. Why would, from what I said so far, you think this would be a disaster for nearest neighbor, right? Like, let's say I have a 256 by 256 image, right? That's pretty darn high dimensional, right? And why does nearest neighbor work well there? It's for a very, specific reason.
Pixels and digits are connected.
It's what?
Pixel and digits are connected.
I think that's part of the answer, but the more general answer that if I understood it correctly, that is getting at is that the digits that you see are not all possible images. In technical terms, the digits live on the effective dimensionality of the data is much lower than the apparent dimensionality. Right? The data is 256 by, let's just say 30 by 30 pixels. Let's say it's 1,000 dimension. But the digits, right? Think of all the images that you could see, right? The images are a tiny fraction of them. So they're actually all fairly close together in this lower dimensional space, which is nonlinear, but still, right? They live on a lower dimensional space. Okay?
Data is sparse.
No, it's not that the data is sparse. Data sparseness is what kills you. But the thing is that, suppose that my space was this room. Okay? Well, that's 3 dimensions. But suppose that all my examples were lying on the ground. Well, then effectively they're in 2 dimensions. We said, if they were all lying on the ground, then I can just ignore height. So the more interesting case is suppose that the examples were, suppose that, this room was very dusty, right? It's the future, the Allen Center has been abandoned, this is covered in a thick layer of dust, right? And the dust particles are examples, right? So the dust particles are occupying a very complex surface, right? There's dust here, and then there's dust there, and whatnot, right? But yet, right, they're living in a 2-dimensional space, right? And so then, nearest neighbor, it is effectively working in 2D. The 3rd dimension never worries it, even though it's not just a question of throwing away one of them. Okay?
So even if your picture was, say, 10,000 by 10,000 pixels, because the effective space is so small, you still don't get hit by the curse of dimensionality at all?
Well, no, you do. So let fast forward to things like ImageNet, right? Have you guys heard of ImageNet? Right? Or never mind ImageNet. Think of recognizing objects in photographs, like in Flickr collections and whatnot.
Yeah.
The dimensional now is much higher. Let's say it's 1,000,000, 1,000 by 1,000 pixels.
Right.
Okay. So even if you're living in a lower dimensional space, that lower dimensional space is still going to be very high dimensional.
Right.
Right? Because also now you're looking at a much greater variety of objects. So even though the images that you see in the real world are a tiny fraction of all the images that you could concoct, but even those are still very high dimensional. So you still get killed by the curse of dimensionality.
So there's a limit to...
Yeah, exactly. Yeah. Okay, so, let's, oops. Okay, we already did this. Yeah. So let's start by dealing with this crucial question of how do you measure distance between examples? Okay? Because if you have a good answer to this, nearest neighbor will probably work well. If you don't have a good answer to this, nearest neighbor will be practically useless. Well, there are many obvious things to use, and this is often what people start out using. So, for example, if you have numeric features, you can use what? Euclidean distance, right? Or Manhattan distance. You know, people what Manhattan distance is? It's the number of city blocks that you have to walk over, right? So it's the, Euclidean distance you square and then you take the square root. In Manhattan distance, you just take the absolute value and then you don't need to take the square root. Okay? It's just the sum of the absolute distances. Or more generally, you can use what's called an LN norm, right? Which is just, a more general distance measure that has Euclidean as the special case for n equal to 2 and Manhattan as the special case for L equals to 1, which is you raise the distance in each dimension to a power n, and then in the end you take the nth root. Okay? So here's a question for you. So the two most widely used ones are n equals 1 and n equals 2, Euclidean and Manhattan. What do you think is the third most used after those two? N equals what? Any wild guesses? This is the answer is interesting, or I wouldn't be asking the question. And it's only good for some applications, but there are applications for which it's just great.
Zero.
Well, n equals 0 wouldn't work, right? Because it
Give you
would.
one.
Because it's
Sorry? Somebody at Microsoft said something? -1. That would be a very interesting. I don't know. I've never tried. It might work. No, it's actually n equals infinity. You know what n equals infinity does?
It'll take it asymptotically to.
So what happens as I increase n is that the larger, component distance is way more compared to the smaller ones, right? Which is what can make me, use one n versus another. So when n goes to infinity, guess what this becomes? This becomes consider only the single biggest component difference. Right? What makes you different is the dimension along which you are most different. Okay? So of course you wouldn't compute it as raising stuff to the infinity because that would be a total waste of time, but it's the same thing. Okay? So that's for numeric attributes. Now there is one important issue here, which is this often works very well, provided that all the dimensions that you're comparing are comparable. So if there are, for example, differences in the gray levels of pixels, then absolutely fine. But if one of them is like your body temperature, another one is your blood pressure, another one is your blood sugar, right? This is just going to be, like let's say I take a distance, and I was measuring it in miles, and now I start measuring in inches, and suddenly the values of that, shot way up. And now this attribute is going to dominate for no reason other than the particular scale that it was on. Okay? So when the different attributes are really not commensurate, then you need to do something else. Okay? And what is the natural thing to do? Well, you normalize, right? You make sure that each feature has a range that is between 0 and 1. Okay? And then they're comparable. Okay? The simplest way to normalize is by range. Okay? So I take the highest value and the lowest value, do the difference, and divide everybody by that. Okay? The result of which the distance is now ranged between 0 and that value, and 1. Okay? Which is that value divided by that value. Okay? You agree? This is okay and it's quick, but it's not very robust. Because suppose I had a cloud of data over here, and then I have an outlier over there, right? Now this becomes the distance, and this is actually effectively rendering that dimension irrelevant. Because all the differences are in here, and they're all going to be close to 0. So a more robust thing to do is to divide by the standard deviation. Okay? So you compute the standard deviation, and now what it means is that if you think of it as being normally distributed, it doesn't have to be. This is all going to be a normal with standard deviation of 1. Okay? This is a really simple thing to do, but if you forget to do it, that might be the difference between success and failure. Okay? There are also problems where it actually does not make sense to do this. Like for example, if all you have here are latitude and longitude, right? They have different ranges, but you don't want to make the latitude and the longitude. If you're interested in the distance between cities, right? You don't want to compress them to the same range because they are different distances. Okay? That's for numeric attributes. Questions? Nothing fancy. Now for symbolic attributes, there's a non-fancy thing and a fancy one. what is the simplest measure that you could use? Let's just think of Boolean attributes for a second, right? If you have a bunch of Boolean attributes, what is a natural distance measure to use? Hamming distance, exactly. I mean, how do you measure the distance between two Boolean vectors? Well, Hamming distance, right? Everybody know what Hamming distance is? It's the number of bits in which they differ. And again, for a lot of applications, this is not too bad. For a lot of applications, however, this is bad. And for a long time, people didn't know how to, solve that problem. And there was actually this notion that, well, nearest neighbor is good for numeric data, where you can use Euclidean distance and things like that. But for symbolic data, you should use decision trees and rules and things like that. And then somebody came up with a very clever idea. And this clever idea is what is called a value difference measure. And this is really answering the following question. Let's suppose that I have an attribute I have color as an attribute. Okay, so my cars can be red, green, or blue. And now Hamming distance is, well, if the Hamming distance is 0 if the two cars are both red, okay? And it's 1 if one color is red and the other one is blue, or one color is red and the other one is green. Because why should one be bigger than the other? But the point here is that for our purposes, sometimes blue is more different from red and green. And the whole idea of the value difference measure is to quantify that. So why might that be the case? And again, people were studying this for like 30 or 40 years before someone came up with this idea, so it's not that obvious. But actually, once you see it, it kind of like makes a lot of sense. And this is the following, is that I'm not interested in abstract notions of how different one color is from another. I don't know if blue is closer to red than to green or whatever. But remember, I am doing this for the purpose of classifying examples. So the question that we really want to ask ourselves is, does red and blue tend to predict the same class more often than red and green predict the same class? In which case, for our purposes, they are more similar. You get the idea? Simple idea, but somehow throughout the 50s, 60s, and 70s, nobody came up with this, and I think it was like in the late 80s that somebody actually had this idea. So here's what you do. So the value difference measure is just a way to compute the difference between two values. So we have these vectors, and now we're looking at the difference in one dimension. And then we can plug that into my, LN norm or whatever. Okay? But the difference between two values is the following. It's the sum over all the classes of the probability of the class given one value minus the probability of the class given the other value. Or to be more precise, the absolute value of the difference. Okay? So if the probability of the class is exactly the same given both values, then they're interchangeable. Right? If the probability that I'm going to give by the car, given that it's red or given that it's blue, is the same, then the two are interchangeable. If I always buy red cars and I never buy blue cars, then the difference is huge, because switching the color from red to blue will totally change my prediction. So if I'm trying to decide whether you're going to like this car because which happens to be red, and and I'm retrieving a car that is similar to it but it's blue. Now that's a huge red flag. There's a certain interference of the red color there, but that means maybe you don't like it. Whereas if you like blue cars equally, then never mind. Okay. Mm-hmm.
What's the n that you're raising that absolute value?
Yeah, again, this is really just actually these are two separate parameters, right? It's similar to the, actually I shouldn't have used n here, but I did, right? So you also want in this individual difference for an individual dimension, you also want to have the power to raise this or lower this. Okay. Again, for the same notion that you might want to have the more important differences dominate or not dominate. So that is also useful here. And typically these parameters get set by, guess what, cross validation. But if you're in a hurry, you can just make it 1. Okay.
So for VDA, we actually have training time, right? We have to train and maintain code.
Exactly. So you're starting to see, well, the training time of this ain't 0 anymore because you need to compute this matrix. Okay. But it's still only linear. So, but yeah, that miracle of 0 time has already disappeared. So yeah, it didn't last very long. Okay.
Does Hamming work only for attributes with a Boolean value like?
No. It's for any discrete address. Again, color, right, is not a Boolean value. So, but the generalization of Hamming distance there is like the distance is 0 if they have the same value. Right? If you have values I and j, The distance is 0 if I is equal to j, and otherwise it's 1. So the difference between red and red is 0, the difference between red and blue is 1, and the difference between red and green is 1,
Okay.
and so on.
Okay.
Okay? All right? Now, these are just the simplest options. In general, you can create whatever distance function you like, and moreover, there will often be a big payoff in creating a very clever distance function. In fact, there's this whole area called case-based reasoning, where people come up with the most amazing programs that just take two cases as an input, and then compute their similarity in very fancy ways. That have like this, if-then-else structure. Like, for example, a popular application for case-based reasoning is help desks. In fact, for help desks, that's the most widely used type of machine learning. It's like, I'm the helpline, for, I don't know, Apple or Dell, and you just call me up saying like, my printer is spewing out garbage, what is the problem? Or my computer won't start, right? And the easiest way to do it is to look up a similar case to yours, right? Because most of the time, the problem that you're having is similar to a problem that somebody had before. But you're not going to do the similarity by hemming distance, I guarantee you, right? Because you're gonna ask things like, well, oh, what is the version of the operating system that you're using? And then depending on the version of operating system, these become two totally different things. I'm like, and what is your PostGit driver, and so on and so forth. So then, then you have a very complex function to finally decide what is the most similar case to yours. And people have spent, huge amounts of, person hours to do this. Yeah.
Is there a machine learning model to predict which is the most similar?
No, you can try to learn, again, people have done it, you can try to learn the form of the similarity function, absolutely. Yeah. We'll see some very basic versions of that, but yes, that's another area of research within the area of research in this learning. Yeah. In fact, when we get to support vector machines, which are really just a very advanced form of instance-based learning, a big area there is learning the kernel design and whatnot. So there you go.
Question.
Mm-hmm.
For the value difference measure, suppose there were two attributes, so red and green are not related, like you can't swap them, but suppose there was another thing, so red color car for Toyota manufacturer and green color car for Honda. These two are very similar, right?
Yes. Good question. So let's say we have two attributes, color and make, right?
Yeah.
What you're actually looking at is an interaction between color and make, which value difference measure does not capture. It makes this decision or this score independently for each attribute. So yes, and in fact, this is what people do, right? But it's important to notice this limitation, right? Is if what happens is like, I like red Porsches, but I prefer blue Hondas. This has trouble with that. So yeah, this is a slightly artificial example, but you can imagine a lot of cases like that. Yeah.
How do people address this?
Well, one way they address this is by deriving attributes, right? They could have an attribute that is a function of both color and make. Or they address this by using other learning methods that are more able to capture these dependencies, like, say, neural network, for example.
When people say they're doing feature engineering, is this the kind of thing that they're referring to?
No, exactly. This is a perfect example of feature. It's like, oh, I know that there's these two attributes that interact, so let me define a new attribute that actually captures the essence of them.
Got it.
It's going from your raw data,
Yeah.
right, to the attributes that actually make your learning easy. This is like the secret of machine learning, is that half of the work, or more than half, is actually still done by you. Right? If you think about it, if you can engineer a derived attribute that is almost exactly the class, then the learning is trivial. And in a way, for example, the whole selling point of deep learning is that you have to do less of that work. For example, when people do vision and speech, right, people have spent decades coming up with better features to use. There's like thousands upon thousands of research papers of better features to use for object recognition or for speech recognition. And the power of deep learning is that you don't have to do that anymore. You can really just start from the raw pixels or from the raw acoustic signal. However, the price of that is that now you have to spend your time tweaking other things, like all the parameters of the neural network and whatnot. So, it's a double-edged sword. Hopefully there will come a point at which you can do representational learning without a lot of tweaking. You don't need to do a lot of the manual feature engineering, but this is research in progress. I mean, as I mentioned in Kaggle, right, according to to the CEO, one of the biggest determiners of who wins is who is more creative about doing feature design.
Right.
Okay, so here's a question. right? So far, we've always said, let's first look at what the representation is and then look at how to learn it. Right? We saw what a decision tree is, we saw what a set of rules is, and what it can represent and can't. But what about for nearest neighbor? What is the representation there, right? I just stored a bunch of examples, but as we know, just remember things doesn't do anything. What is the frontier between the classes that my database, together with, say, my Euclidean distance, is really representing, right? We're not going to compute it explicitly because that's, a pointless cost. But we should understand what is it that implicitly is being represented there. Okay? And then we will understand what nearest neighbor is all about. And then we'll actually be able to understand why it can be so powerful. And the crucial notion is the notion of a Voronoi diagram, which you may have met in areas like computer graphics and whatnot. What many people have heard of Voronoi diagrams? Yeah, that's quite a few of you. Okay? So we're going to look at Voronoi diagrams. Of course, we're going to be doing them in much higher dimensional spaces, but the basic idea is the same. So here's the idea. This little rectangle here is my training set. Okay, so I have my negative examples, I have my positive examples, and then XQ is going to be my query, right? I want to classify my query. Okay. So first of all, what is a Voronoi cell? The Voronoi cell of a training example is just the set of all points that are closer to it than to anybody else. It's the region in space where it wins. Okay. If this room was the instance space, and each one of us was an example, right? I would win everything around the lecture, okay? You would win, for example, you would win this region here, and halfway down the aisle, and then she would start to win, okay? So you would actually have a bigger Voronoi cell than him, luck of the draw, okay? So this is the notion of Voronoi cell, and now is what is important for us. So you can see why this would be important for nearest neighbor, right? Because the Voronoi cell of an example is the set of points that it is going to classify. If the query falls in my Voronoi cell, I determine the class of the query. Okay? So finally, what is the region of each class? It's the union of the Voronoi cells of its instances. Right? So for example, let's say that this was positive, this was negative, negative, positive. Right? What would be the region of the positive class here? It would be this region, right? It's the union of the Voronoi cells of the positive examples. Everybody agree? And notice that the Voronoi cells, if you're using Euclidean distance, which I'll assume we're doing, I'm going to assume, unless I say otherwise, that we're using one nearest neighbor and Euclidean distance. The same notions still apply in other cases, but they're harder to picture. So. And again, the classic studies and theory have all been done in that same. Okay? So if I'm using Euclidean distance on my nearest neighbor, right, what is the dividing line between two Voronoi cells? It's the straight line composed of the points that are at the same distance between the two points, the two training samples. Okay? Which, as we know, is a straight line because 2 points determine a straight line. Okay? Everybody agree? So now if I give you a database of positive and negative examples, you know that it implicitly it's forming this, jagged frontier between them. Okay? And that is really the representation. And now you can see that as I add more training examples, the frontier can actually get arbitrarily complicated for free. And it's not even axis parallel as in decision trees, right? It can point in any direction. Well, this is incredibly powerful. At the same time, here's another way in which it is powerful. If all you have is 2 examples, let's suppose that I had like one positive example here and one negative example there. All of the other methods that we're going to look at would be totally stumped, right? Your pre-pruning wouldn't even let you start with your decision tree, right? Nearest neighbor would say well, sure, here's the border. That's the problem. And if you think about it, this is probably not a bad place to put the border. Okay? I mean, as you get more example, that's probably going to shift, but this might actually classify correctly everything over here and everything over there, so that's actually quite nice. Okay? So despite its simplicity, nearest neighbor is actually surprisingly powerful. Questions?
So Voronoi cells can be disjoint, right? For a particular class?
No, so remember that, let me make sure I understood your question. The Voronoi cells are all disjoint, right? Because each Voronoi cell is, no point is won by more than one example. Of course, there are these ambiguous points that are at the same distance, but they have, measure 0. Okay? And then the class is your union. The region of a class is the union of them. Okay? So the regions are all disjoint. Was that your question?
So
There is no overlap. Mm-hmm.
there is no overlap, but in this particular example, if you union them, they appear to form one particular region. But
Oh, no, that will
always-
generally not be the case. So, for example, let me give you a different example. Let's suppose that this was plus, and this was plus, and this was minus, minus, minus. Right? So now the positive region is actually composed of two different clusters. And this happens a lot.
Yeah.
Right? In fact, this is why it's useful to have things like nearest neighbor. If there was just one border between them, then there are simpler methods that would work just fine. Okay? Yeah.
How's that when X selected?
No, so X is your query.
Oh, okay.
Right? Think of this as a map, right? And I'm giving you a new point on the map, and I'm saying which class does it belong to, right? And like the reason I have this circle here is I think of the XQ as like you have a here's another metaphor, right? You have a lake, okay, and this is the surface of the lake, and in that lake there are pebbles that some are painted red and some are painted blue, right? And now you drop your query into the lake somewhere. Your query is just a random, new pebble that was dropped in the lake, right? And then a ripple goes out from the pebble, and the first colored pebble that it hits, that's the class that wins. If the ripple from that pebble, hits a positive one first or a red one first, then this is red class.
And those pebbles that were training samples.
Yeah, exactly. The pebbles are the training samples, and the query is the new thing that you're dropping there. That's this a very poetic metaphor. But I think it helps, right?
But if we have k valued and if we're taking, in your first slide you mentioned we can take if the class value is real.
Yeah, exactly. Yeah, this is for the classification case, and again, similar notions apply with real values, but it's more complicated. So yes, what I'm going to do, for the time being, is classification, two classes even, Euclidean distance. Kind of like the simplest you can imagine, one nearest neighbor. Okay? Okay, so I've told you that nearest neighbor is surprisingly powerful. Okay? And now let's just see exactly how powerful it is and why. And in fact, the history of this is very interesting. This algorithm was invented in 1952. There are really two things that made it become popular. One was that as the 50s turned into the 60s, computers got more powerful, but the other one was that a couple of people didn't trust it. They were used to these statistical algorithms that had guarantees. Right? Well, in the limit of infinite data, this will give me the right answer. And nobody knew what the heck nearest neighbor would do in the limit of infinite data, right? It might do something completely crazy. And then a couple of people actually proved that in the limit of infinite data, and by the way, what most statisticians do for a living is make these assumptions and show that you get the right answer in the limit of infinite data. Right? Jerry Friedman, who's a famous statistician and one of the co-inventors of decision trees, he says that most statisticians live in asymptopia. Which is the utopia that you get to when you have infinite. They never, worried about if you have infinite data, then you also have an infinite computational cost, right? But then, of course, when computer scientists got involved, that changed. But the thing about nearest neighbor was that it was when people actually showed. It was these two guys, Tom Cover and Peter Hart. They actually proved. They published a paper in 1967, I think, or 1960, late 60s, that showed that nearest neighbor actually converged, or more generally, k-nearest neighbor actually converged to the right function when you give it more and more data. And some of the people were like, "Oh, wow, this is amazing. This is an algorithm that it doesn't have the modeling assumptions that the old statistical algorithms did, and yet it has similar guarantees." And they had, this was an 8-page paper full of math, but actually the core of the proof is so simple that I have it all here in one slide. In, 1, 2, 3, 4, 5 lines. So let me give you those 5 lines because I think it's kind of enlightening. So here's what we're interested in. We are interested in epsilon star of x, which is the error. Star is usually, the notation for optimal, right? So epsilon star is the error of the optimal prediction, often also called the base rate, meaning you can't possibly do better than that. If I've seen infinite examples, and 60 and of those that have a particular set of attributes, attribute values, 60% are of the positive class, and 40% are of the negative one. What is your best prediction? And that error is unavoidable. There's no amount of, I already have infinite data, hypothetically, right? There's nothing else short of like gathering new attributes that will have more information that will change that, okay? So there's the error of the best possible learner, right? If you could somehow see what the best possible model is, this is just the noise, the limit set by the noise level, okay? So this is what we're interested in, is the error of the optimal prediction. But of course, we are using nearest neighbor. So what we have is the epsilon and n of x. This is the error that the nearest neighbor algorithm makes if x is the query point, okay? And ideally, we would like them to be the same. In which case, nearest neighbor would be the optimal algorithm, and we could go home and ignore all the other kinds of learning, except that they have similar theorems. But, right, so that's the question that we're trying to answer, like, what is the relationship between the error rate of nearest neighbor and the error rate of the optimal classifier, okay? So, and here's the result. As usually in math, first we give you the result and then we give you the reasoning that leads up to the result, right? Even though that's often how things happen in practice. So here's the theorem. As n, my sample size goes to infinity, the error of nearest neighbor goes to at most twice the optimal. Okay? Which means that if the optimal was, say, 4%, sorry, if the optimal was, say, 2%, right? 2% is the best error rate, is the lowest error rate that any classifier could have. Nearest neighbor will give you 4%, which is pretty good. If the base rate was 20%, then nearest neighbor is going to give you 40%, which is not so exciting. But as when we get to k-nearest neighbor, we'll see that you get, with k-nearest neighbor, you're actually going to converge to the optimum. So k-nearest neighbor, if you do things right, is actually the optimal classifier if you give it infinite data, which means if you're an asymptote. But hey. So what is the chain of reasoning? Very simple. When will nearest neighbor?
So when you want to compute the error, why do you consider prediction, not training?
Because remember, predictions are what we care about, right? Error on the training data, all you have to do is remember the data and spit it back out when you get a question.
But it's more sensible to compute it because you want to train a model and you want to compare it with other models.
No, yes, but remember, the reason why we're doing this, as theory is that you don't have access to the test data. So what we're going to make here is a statement about what will happen in test data even though we haven't seen it. Which is nice to have. In practice, you don't know, so you do things like cross-validation and whatnot, right? But why is this result useful? This is all useful because it lets us trust that nearest neighbor will do the right thing as you give it more and more data. And I think it's enlightening too, just from the point of view of the intuitive understanding of the algorithm. But it's not something that has, you're not going to use this as a subroutine in your algorithm, if you will. Okay, so when does nearest neighbor make a mistake? There's two different ways in which you can make a mistake. One is, the example was positive and it predicted negative, right? That's a mistake. What's the other mistake that it could make? The example was negative and it predicted positive, right? So, to put that in math, the error of nearest neighbor is the probability that the example comes out positive, right? And then the nearest neighbor predicts negative, right? And the two things are, by hypothesis independent, so the probability of that is P of plus times P that NN predicts plus, okay? Plus the same thing for the example being negative and nearest neighbor predicting positive, okay? So we're at this line. Everybody happy with it? Okay? Now the next thing is simple, is to just realize, well, P minus is the same as 1 minus P plus. You agree? Because P minus plus P minus plus P plus are 1 because, the example has to have some. And same thing for the prediction, right? P and N minus is the same as 1 minus P and N plus. You agree? Which means that I can just express this all just as P plus times 1 minus P and N plus the same, plus the same thing but in reverse line. Okay, you agree?
Yeah.
Okay. So again, this is just a very simple substitution. Okay. Now here is the crucial point. What happens is my data set size goes to infinity. So here's my query point, right? And here's my nearest neighbor sitting around somewhere, right? What happens to the distance between them as I get more and more data?
Reduces.
It shrinks, right? Because when I get more data, right? In the worst case, that guy is still the nearest neighbor, but generally, at some point, some new point will show up that is closer, right? So as I get more and more data, these 2 points, the query point and the nearest neighbor converge to the same. This is the crucial observation, right? So finally, if I have infinite data, guess what? They are on top of each other. Okay? And if they're on top of each other, then the probability that nearest neighbor predicts plus becomes the probability that it's plus. And the probability that nearest neighbor predicts minus becomes the probability that it predicts minus, because we are now at the same point. These are now the same probability. Everybody agree? Therefore, we can replace one by the other, so let's do that, right? I can go to this expression and make these replacements, and what do I get? I get p plus times 1 minus p plus, right, because this has converged to p plus, you agree? And I get the same thing on the other side. Okay? And notice again that these two expressions are the same, except that I flipped the order of the p and the 1 minus p, right? And notice moreover that either the true example is positive, right, in which case this is the error, right? Or the true example is negative, right, in which case this is the error. But either way, what you end up with is that this is the error times 1 minus the error. Right? Which one lines up with the error, whether it's plus or 1 minus plus, depends on whether this was a positive or negative example, but the expression is the same. So what you end up with just 2 times the optimal, right, because this is, we do have the real p, right, so this is the epsilon star. This is going to be 2 times epsilon star times 1 minus epsilon star. You agree? Because either epsilon star is p plus, if the majority class was negative, or it's p minus, if the majority class was positive. And then just to make the math simpler, right, we're just going to, drop this guy, right, and turn it into a bound. Oops. Okay. 1 minus epsilon is necessarily less than 1, so this whole thing is necessarily less than 2 epsilon star. Do you agree? So I just proved that when my data set size goes to infinity, the error of nearest neighbor converges to being upper bounded by twice the optimal error. Pretty amazing. Any questions?
So, but for it was computed by statistics that this is the optimal error.
Mm-hmm.
There's another theorem that proves that, but we're not seeing.
The theorem that proves what?
There is another theorem that was proved before that by the statisticians that this is in fact the optimal error.
No. Like I'm saying that there is an optimal. Look, there is an. We have to define optimal error, right?
Yeah.
The optimal error is the lowest possible error that any classifier could achieve. This is a purely theoretical notion because no one will ever know what it is. And I'm just saying, like, how close can I get to that theoretical quantity? But I still don't know what the epsilon is, right? At the end of the day, I can't take some value from somewhere and plug it in there. Unless I generate the data myself, which is useful for algorithm testing, but not for real data science. Okay?
So can you talk about?
Mm-hmm.
Can you talk about what the last but one line means?
This line?
The Gibbs classifier.
Oh, I haven't gotten to that yet, but so Gibbs classifier is actually this. The Gibbs classifier actually. Let me not tell you. Let me defer that until we actually talk about the Gibbs classifier. So, but in order to not leave you too much, we will talk about the Bayes classifier and the Gibbs classifier when we talk about Bayesian learning. Suffice it to say that, the Bayesian classifier, as we were just talking about, is a purely theoretical notion. There is, however, a practical notion, which is, the Gibbs classifier. And this is a classifier that just picks a hypothesis with probability proportional to its posterior probability, right? And the Gibbs classifier has this property that it gets at most, even though it's a physical thing, it has this, and a simple thing conceptually, it has this property that it achieves at most twice the error rate of the Bayes classifier. So another way to say it is that what we just proved is that in the limit of infinite data, nearest neighbor converges to the Gibbs classifier. Okay? Not that interesting at this point, but just make a mental note for when we talk about Gibbs classifiers, and then and then what comes from this is that actually nearest neighbor is a valid implementation of the Gibbs classifier. Okay? So it's not the theoretical best algorithm. In some ways, it's like the closest you could get to the theoretical best with just a real learning algorithm. Okay? Unless, of course, you are allowed to make further assumptions, in which case the algorithms that make those assumptions will do better. But the beauty about nearest neighbor is that it didn't make any modeling assumptions. It didn't say, each class comes from a Gaussian distribution, which is what people tended to do in statistics pre-machine learning. Somebody else has a question?
So you're comparing the nearest neighbor, error rate, range, with this theoretical optimal.
Mm-hmm.
And so is this how we're going to be doing this, like for every other, like the next ones you're going to learn, we're going to do the similar thing, doing the same theorem?
You mean for other algorithms?
For other algorithms, they're going to be doing the same.
Other algorithms, by the way, decision trees also have proofs like this for the same kind of thing, but they're very different because the algorithm is different.
So can I infer from this that if you have an infinite amount of data, that you shouldn't pick E and N because
no, you should not,
or should not?
Well, exactly, but unfortunately, what happens is that neural network people say, I have a theorem that says with infinite data, neural network is perfect, so I don't need to know anything but neural networks. And then instance-based learning have this theorem, and the support vector machine people have what they call the representative theorem, and the decision tree people, Jerry Friedman and Leo Breiman, they proved something for decision trees, right? And what people don't realize is that only gets you to step 1. Because this is if you have infinite data. And our way to look at this is to say if you have infinite data, life is good. But in the real world, you don't have infinite data. What this means, however, is that these learners are much more powerful than the other things that people do. They have a fixed representation space. So, for example, linear classifiers. Very popular, many machine learning classes spend the first 2 or 3 weeks talking about linear classifiers. And we will talk, about a couple of linear classifiers here. They're fun, but linear classifiers don't have this property, right? If the real frontier is nonlinear, as almost all of them are, it doesn't matter if you give it infinite data, it'll still learn the wrong frontier. These algorithms like k-nearest neighbor, decision trees, sets of rules, multilayer perceptrons with enough hidden units, support vector machines, graphical models, blah, blah, blah. They have this beautiful property that if you give them infinite data, they can learn the right function. So this makes them better than those other ones. They have other offsetting issues that we'll talk about when we'll talk about learning theory. But this doesn't tell you how to decide among them. If you have infinite data and you didn't care about computational cost, then what this theorem says is, well, use any one of them. But in reality, you never have infinite data. Even if you have very big data, in the exponential size of, when you have more data, the dimensional area space also usually goes up. So this only gets you to square 1. Yeah.
So I have the strange thing about infinite data is, unless you know how close you are to having infinite data, it's the so that's the strange thing with.
Well, infinite is a very strange notion if you think about it. Yeah.
Right. It sort of means that you're still only able to measure against the data that you have.
Yeah.
To see how well you're doing.
So these at the end of the day are theoretical notions because in practice you never know if you're in that regime. But remember, infinity is not a number. Infinity is just a shorthand for a number that is so large that it doesn't matter how large it is. And that's what it means here, is that you have so much data. Infinity, which is the point at which having more data will not make any difference. So there is no infinite state, right? But you're right that can you come to me and say, well, are you close enough to infinity? In these models that make parametric assumptions, like say things are Gaussian, you say, well, how much error are you willing to tolerate? And I'll tell you how much that is enough. But for something like k-nearest neighbor, you don't have that. And again, for something like all these classes of powerful learners, which is really what the whole point of machine learning is, you don't have that. Which is why these types of theorems are much less popular in machine learning than in stats. In machine learning, what people use is what are called finite deviation bounds, which is proofs for finite data. And we'll study that when the time comes. So we do have a whole branch of theory that deals with this more realistic setting. But having said it is true that 90-something% of statisticians spend their time doing this kind of thing, and it has a certain trust value. I mean, one of the big problems in machine learning is people don't trust what the algorithm is doing because they don't understand it, and having theories like this can be very reassuring. Yeah.
So, earlier on, when you were elaborating on this, you said, you made a point about the probability of, if it is 0.2, then 2 times the 0.2, 0.4 is pretty good, and then said, but if it is 60-40, that's not so good.
Mm-hmm.
So then, what can we infer from that? Does it mean then that for...
What we can infer from that is what you really want to use is k-nearest neighbor. Which brings us to the next and even better theorem, which is the same theorem but for k-nearest neighbor. And now the statement of the theorem is a little tricky, and I'm not going to do the proof again because you will see why this still holds. Right? And here's the theorem. If n goes to infinity, right, same as before, infinite data, and the k in k-nearest neighbor also goes to infinity, okay, but the ratio between k and n goes to 0, right, you're getting more and more data. Right? Think about it this way. Let's say that k is the square root of n, or log of n. Let's say that k, for k you use log of n. Okay? So as n goes to infinity, k also goes to infinity, right? But the ratio between them goes to 0. Okay? You can make things be this way, right? It's completely feasible, right? In that case, lo and behold, the limit is the optimal error rate itself. So nearest neighbor is only as good as the Gibbs classifier. K-nearest neighbor is as good as the base classifier. It's the best that you could ever do. Okay? Now, can anybody guess, can anybody give sort of like the qualitative argument as to why this is true? Brownie points if you do that.
Excuse me.
If there were points for class participation, this would give you a notch right there. Yeah. Uh-huh.
I missed why k divided by n approaches 0.
Yes, that's crucial. And I haven't told you why. I'm asking you why.
Oh.
And this is all here for a reason. We're going to get to it shortly, but it's always better to discover things yourself. Yeah.
So when k by n is tending to 0, you are essentially learning in subsets or learning in patches
Sure.
over the space.
That's halfway there, not the whole way there.
Is it because k can never be infinite because it's always limited?
No, it could be. I could make k equals to n. But that would be a boring result. That would give me the base classifier, I guarantee it. Remember how this proof went, right? What happened was that as my nearest neighbor gets close to the point, right, the probability becomes the same. Okay? But the problem is that it's still only one point. What I would really like to have is not just one point at the query, one neighbor at the query point, but an infinite number of them. In each case, the fraction of those near neighbors that was positive would be an accurate estimate, in fact, a perfect estimate of the real probability of plus. Right? Let's just think about one particular point x out here in space, right? And I have infinite data, right? So it's an embarrassment of riches. I have infinite points piled up right there. Okay? Nearest neighbor is kind of dumb because it only uses one of them. Right? If I have 1,000,000 points here, let's just say 1,000,000 for the sake of argument, and 800,000 of them are positive, that means that my probability of positive is 0.8. Right? And again, if as this goes to infinity, that becomes the exact probability estimate. Do you agree? So at that point, I know the true probabilities, and so I guess according to them. And this is it. And so I predict whoever's the majority according to the true probability. And guess what? That's the optimal. Okay? Now, why did I need these three conditions? Well, I need infinite data, obviously. I need my k to go to infinity so that my probability estimate from the nearer neighbors that are all now at the same point is perfect. Right? I need the k over n to go to 0 so that I am in an infinitesimal region. Right? If my k over n didn't go to 0, I might still be averaging over a large region, in which case I am now incurring an error. Okay? So this actually incurs that the region that is spanned by my k nearest neighbors actually shrinks to a point. So this ensures that the region shrinks to a point, and this ensures that I have infinite samples at that point, at which point my estimates are perfect, and I have the optimal classifier. The only reason I need n to go to infinity is that k goes to infinity at every data point. Okay?
Well, then n has to be more infinity then.
Well, but precisely. This is what, that is the English version of this statement. K over n goes to 0, as n goes to infinity. There are different degrees of infinity, right? This is like when math is fun. And this one line here was a whole other paper from Cover and Heim, which only took it to the next level of excitement.
And the training and classification time goes to infinity.
Well, this is what the statisticians never worry about, right? Bless their heart, right? They leave it to us. But but we're good at that, so actually no, it's all good at the end of the day. Yeah. But just as an aside, right, this is why, for example, I don't use the Friedman, Tibshirani, and Hasty textbook in this class. Because it's a book by statisticians. On some chapters they have a one paragraph section at the end entitled Computational Issues. And in some chapters they don't even have that. So it's a useful book, but it's not the whole picture.
So if you did not have that third clause, what would be the answer?
No, exactly. If I didn't have that third clause,
if you didn't have k over n going to infinity, up to 0.
Then what happens is that the region that was covered by the nearest neighbors wouldn't just be a point. So you would be averaging over a region. And then when you're averaging over a region, you are making errors. I mean, increasing k in a sense is like, having an increasingly fuzzy image. Right? You don't see where the frontier is because you're averaging over things on both sides. Okay? All right, let's take a break. It's 8:15. Let's continue at 8:25.
Perfect. What is saying?
Everything
So what was that?
Where do they show our embedded in the optimal?
This whole little was a sim.
But I had that.
And the attributes, they're just whatever describes the data. Where the difference in the attributes the weight can be. If I said one star will be lower than if I have a worse set of attributes. Yeah, so they make a huge difference. That Euclidean is a metric. And all these terms only apply if you have a metric. Although sometimes people use a measure. And this when I said value difference measure, it's not a value difference metric. Which means that if you're using a value difference measure, right, it actually doesn't, this doesn't apply to it. And now, and we know what the fairly case is like, so, blue Hondas, but you like red Ferraris and things like that.
Well, it will
So if you're comparing architecture, one is 5 years If you don't distribute something, so every yeah. But you're doing more like data, that's your training.
Okay, so I'm just completely get it wrong because I'm basically what I'm doing is I just think of oh, interesting. So that you could okay. Yeah, because I noticed that the data is changing because like the more I trained with like non-local correlation, we're having more in the data set is changing. Okay. So I'm right now one of the 400 rows of those last 800 are in my foundation set. The other 400 is what I need to. Okay, so I need this. One of the guys that we're doing I assume so for confidence of I should just try this I don't like I haven't seen anyone like
Well, it's the best contrast. So you get the best contrast from black against white.
That would probably
So it's all black. Oh, so they look for the notes.
Like we find that very
that's a good point, actually. You mean use, I agree with you, actually. I've just never thought of it. So thanks for the suggestion. Yeah, I could use blue. Yes, that's a good idea. If I forget what I need, I can use multiple colors and yeah. This reminds me of some of my graduate students saying, like, why do you always make notes in you know, on the papers that we write in black? And then I actually got myself to red pen. It feels like you're marking an exam or something. Like, but it is easier to read. So it's the same principle. They should have had the opposite convention and so they didn't.
Yeah, so if we divide
sometimes things are so bad that they would do it. Right? Yeah.
So if we did all of that, I'm sufficiently yeah, I'm traveling a week for business. I'm just on my plane.